Okay, my friends, so I started Googling to try to figure out how deep Todd Lake is. And I knew going in that it was going to have different depths along the way because all lakes are like that, right? You can, generally speaking, when you walk into a lake, it's very shallow on the edge. And then as you walk further, it gets deeper and deeper and deeper. What I think is really cool about Todd, though, is it's got a number of different shallow areas and a couple really deep spots. So just for reference, Bachelor is going to be off the bottom of this map and Broken Top's off the top. So usually when people walk in the trail, they come in this way from the parking lot and they hit this part of the lake first. And you can see, I'm going to zoom in, move the map around and zoom in a little bit. There we go. Oh, this is super cool. Look at all that detail you get. So I'm assuming that 1 and 2 and 7 and 13 and those are foot markers. That's how deep the lake actually is. You've got these deep areas here that's like a 60-foot deep part of the lake. What if we can zoom? Oh yeah, there's 60 feet. I'm zooming way in now. This is really cool. So it looks like, okay, the lake looks like it bottoms out around 60 feet. Okay, and these are single foot markers, and it gets deep pretty fast. These lines, it gets deep pretty slowly. These lines very close together show that you're increasing in depth pretty quickly. So 1 to 2 to 3 to 4, that's happening pretty quickly. I'm not sure what the scale is on this map. I don't see it anywhere. It doesn't really matter. And then what's cool though is down here, it gets kind of shallow. This is interesting. Like at this narrow point between the two kind of pools of the lake, it's got this cool like shoulder that's only 9 feet deep. So if you couldn't walk across it unless you were 10 feet tall, but that's super shallow. And then it's got this other deep section up at the top that looks like it drops down to about 22 feet. Very, very cool. Exceptionally cool. Now, the problem, of course, is we need a height. We don't need a bunch of heights. We need a height. And that's where I want to teach you about something, a mathematical principle. You know what? Let's just go to the chalkboard and talk about this. Okay, friends. So, volume is basically length times width times height, as we mentioned in the exam. But there's only one kind of shape that is exactly equal to length times width times height when you're finding its volume, and that's a cube, or a box, a rectangular prism, I believe is the technical name. That's why you have to use other formulas for things like the cone that we just did for Mount Bachelor. And there's other formulas for different shapes like spheres and, cylinders and things like that. But how about a weird shape like Todd Lake? Well, here's the thing. Todd Lake, we're not going to talk about the depth at first. I want to talk about that surface area that you figured out back in the previous couple questions. Todd Lake's got that kind of cool shape where you've got the kind of the section up here and then the big section down here. Now, you just Googled the surface area of this in acres, and it was 45 acres. So it covers 45 acres. And then I had you convert it to square feet, but I don't remember what that is, but let's just talk about 45 acres. If you're calculating the volume of something, you need to know the length and the width first, multiply those together, and then multiply it by the height. But the math doesn't really care about the dimensions of the shape you're doing the length times width of. All it cares is what is the answer to length times width. So when you visualize the volume of a shape like Todd Lake, you can sketch, say, a square or a rectangle that has exactly the same coverage as Todd Lake. So if I look at that, and I look at that, they appear to cover about the same. This is a more beautiful natural lake, but that is an easier calculation to visualize. So the math doesn't care if length times width equals 45 acres, or if whatever the hell you'd have to do to this to get 45 acres. I'm sure that nobody did length times width on Todd Lake. What they did instead was take aerial pictures and all kinds of fun data analysis to figure out that's 45 acres. But the math doesn't care. So you can just squish this or stretch it until it has this shape and it covers the exact same area. We can do something similar with the depth. Give me a second here. Let me clear the board, and we can do the exact same kind of thing with the depth. Okay, so what I've done here is a very crude drawing of the surface of Todd Lake in blue. And then Bachelor's that way, Broken Top is this way. This is kind of like that 20-foot section that dropped, and this is that little narrow channel I was just talking about, and here's that huge 60-foot section that drops off. We can pretend the surface is a rectangle with a top of 45 acres. The problem is the height, or in this case the depth, which is acting as the height, is not uniform at all. It's very deep in some places, extraordinarily shallow in others. This is also a two-dimensional vision. This lake would actually be covering a third dimension coming out like this. So you'd have these big bowl-looking things, and that gets challenging. It would be nice if we could pretend that the top of the lake were that 45 acres. And it would be nice if we could pretend that the depth had a uniform distance. It's clearly less than 60, and it's clearly more than 1. It's got to be somewhere between that 60 and that 1. But if we could figure out what that distance would be to pretend Todd Lake was just a big box of water, then we could just do length times width, which is 45 acres, or whatever many square feet that is, times whatever that depth was, and that would give us our cubic foot measurement. Now the challenge is figuring out what that depth is. So what you have to do is you have to think about what an average actually does. When you calculate the average of a bunch of numbers, you add them all up and then you divide by how many there are. We've talked about this a couple times in this class. What that is really doing is it's spreading out the numbers evenly. Like, for example, if somebody has $2 and somebody has $10 and you add those together to get 12 and divide it by 2 and get 6, what that really means is the person that has $10 gives 4 over to the person that has 2, and now they both have 6. That same logic can be applied with these depths. What you can do is you can take some of the deep water and donate it, if you will, to some of the shallow water. So what that's going to do is it's going to make the shallow water deeper, it's going to make the deep water shallower. And you can just keep doing that. You might say to yourself, oh, well, this water here needs some more added to it, so I'm going to take some more water away from the deep water, and I'm going to add it to this shallow water. Now, you got to realize, this is a very, very overly simplistic idea, because this is actually a three-dimensional lake that I'm doing this to, so just so you understand. And also, we're not going to have to do this. You're going to Google this in a second. This is a well-published number. I found it a couple different places. We're still not done because we've got all that water over there that needs, this is all a 1 and 2 foot deep section of the lake when you first walk up to the trail. So I think we have to give some more of this water. And eventually, if you keep giving from the deep up into the shallow, you'll eventually get to the point where it's all the same depth. And of course, this would be in 3 dimensions. That's called the mean depth of the water. Mean, M-E-A-N, means the same thing as average. And that's something you can Google. And that, once you know that the average depth is whatever that is, you're going to find in a second, it's still the same total amount of water if you pretend everything is that average depth, versus pretending it's actually what it is, which is that previous sketch that we saw on the fishing map that I looked up. But this is mathematically easier. So now you have the situation where you can envision the surface area as a rectangular 45 acres or whatever square feet, and then you can envision the depth as that average depth. This idea is a takeoff on something called Cavalieri's principle. One of my fellow Italian mathematicians came up with that a few hundred years ago. You don't need to know that. But once you know the average depth, you can use it to calculate the volume of the lake. Go find that now.